Hello class, this is Ms. Riggins with today's video on section 4.7, LHopitals Rule, Growth and Dominance. As you're watching the video, please remember to write down important notes, equations, formulas, statements, or questions, and feel free to pause, rewind, or review the video as often as you need to get a better understanding. When you have completed watching the video, please write down a summary, brief, about the video as well as the top question and submit that via the online WISC form. All right, let's begin. Today we're going to actually take it back to some limits and definition of derivatives. And so let's take a look at this particular function. Now if I gave you this function, then the first thing you guys will probably do is try and evaluate this algebraically by substituting x equals 0 in for the numerator function and the denominator function. But when you do that, you end up with something that equals 0 over 0. And some of you may say, oh, well, that means the limit does not exist. But that's not really true. This just basically means right now we don't know what the limit is. And the fact that we evaluated algebraically and ended up with this tells us that there's something we need to look at a different way, because right now evaluating this algebraically does not make sense. And so the second thing I think you would probably do would be to take a look at the graph of this function as x approaches 0. And as you can see, as x approaches 0, the function values from both sides both seem to be approaching 2. And that makes sense from this graph. But I know you're saying, well, x equals 0 is not even part of the domain, and you're absolutely correct that there should be an actual hole here because x equals 2 is not part of the domain. And when I were to evaluate x equals 0 into the function, I would get undefined. But as we can clearly see that the function values do seem to be approaching 2 and not 0 over 0. So some of you may be wondering, well, why is it that we get 0 over 0? Well, the reason why we get 0 over 0 as x equals 0 is because in both the numerator and the denominator function, they both evaluate to be 0 at x equals 0. But remember, the function f is really a result of dividing the two functions. So something happens when you divide the two functions to have it end up being equal to 2. So what you may have learned from this is that, again, 0 over 0 as a limit value doesn't really tell us much about what's going on with the function, and that we may need to revert to a graph of the function to be able to tell us what the limit is. And some of you may already be saying, well, what if we don't have a graph of the function? In other words, what if we aren't able to graph this on a graphing calculator or Desmos or things of that sort? Well, there is an algebraic way to evaluate this limit and get the correct answer, but it does involve something that we have not discussed before, which is called linear approximation or local linearization or tangent line approximation. So if you remember, when we started talking about the derivative of a tangent line, the derivative of a function is the slope of the tangent line of the function at that point. As you can see here, this seems to look like the graph of what's going on. And as you can see, the function, this curve thing, is not equal or is not the same as the line of the tangent line. But what if we were to make h really small, a lot smaller than this? Let's see what would happen if we were to make h, let's say instead of this long, let's say we were to make h this long. So if we were to make h this long, and then around this little h bubble, if we take a very good look, if I were to zoom in, it seems like the function and the tangent line look to be right on top of one another. Now, of course, we know them not to be exactly equal except at the point c comma f of c, but it looks very, very close to one another. And so we can approximate the function, the curve function, with a tangent line, and we call that a local linearization. And if I were to zoom in on any function value, on any function, if I zoom in close enough, it would look like a line on my graphing calculator or on Desmos. And so that's what we're going to use. The idea is local linearization. It says that for very small h, we can use the tangent line of the function at that point as an approximation of that function. Well, we're going to use local linearization to solve that 0 over 0 problem. So let's take a look at two functions that have certain conditions. Number one, if I take a look at the quotient of these two functions, in order to use this tangent line approximation, we need to first guarantee that these functions are differentiable at that point, and we're going to call it A. Because if it's not a differentiable at that point, then we won't be able to find the slope of a tangent line. So therefore, we need the functions to be differentiable. So that's one of the first things we need. And they have to be differentiable at that point A, where A is in the domain of both. And then the second condition that we need, and you'll see why a little bit later, is that the functions, the numerator and the denominator functions evaluated at that point A are both 0. And as you can see, we have that with our problem that we had earlier. So let's actually say that when we take the limit of the function, it seemed that it would be equal to 0 algebraically, but let's use linear approximation to apply the limit. So let L sub f and L sub g be the linear approximations for both f and g at A, okay? And the only condition is that x has to be very, 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 very close to A, because if not, then it's not really a good approximation of those two functions. And just to refresh our memory, f prime of A is the slope of the tangent line of the function at that point A, and g prime A is the slope of the tangent line of g at A. And then f of A is the coordinate A comma f of A that's part of the point, part of the graph as well as part of the function. The same thing with g of A. Okay, so now that we know that for very, very close x to A, that the linear approximations of these functions can be represented as such, then we can write the limit function like this. And then therefore we can write it like this. And then we can say, if you remember that f of A and g of A both have to equal 0, so we can cancel out f of A and g of A, and we end up with this. And as you remember, x is very, 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 very close to A, but it's never going to be equal to A. So this ratio right here is always going to be 1 for any x that's very, very, very close. Well, for any x that's not A. So we end up with something like this. Well, this is powerful because what this means is that the limit of the quotient of these two functions is equal to the limit of the quotient of the derivatives of those functions evaluated at that point A. And this is what is referred to as LHopitals Rule. And the conditions for LHopitals Rule are the same conditions we talked about. F and g have to be differentiable at that point, x equals A, and f of A and g of A must equal 0. And the additive condition that we didn't consider at first because we didn't know about it was that the g prime of A can't be 0, because if that's the case, we won't be able to evaluate the limit using this method, because g prime of A in the denominator will come up with a undefined limit. And then all that LHopitals Rule says is we can take the derivative of these functions at that point A and take the quotient of those derivatives and get the answer for the limit. And that's actually what we can do for this situation. So when we apply LHopitals Rule to our original problem, we find that we can take the derivative of the numerator function, which is 2e to the 2x, and the derivative of the denominator function, which is 1, and evaluate them at A, which in our case is 0, and we end up with the answer being 2, which is consistent with what the graph of the function was doing as x approached 0 as well. So it's important to note that LHopitals Rule can be used only in the case, though, when you have some type of problem, when you get a form that doesn't look right, like we saw, which was 0 over 0. But in general, if I had the time to show you, we can apply it to many forms besides just 0 over 0. Your book talks about the forms between 0 over 0 or infinity over infinity, but actually any indeterminate form, which looks something like this, you can use the LHopitals Rule. If you try to compute the limit algebraically and you end up with something that looks like this, you can apply LHopitals Rule to that to be able to solve it. So let's move on to the last thing I want to talk about. If you remember in pre-calculus, we talked about in behavior as functions went to infinity or negative infinity, and how certain functions grew faster or grew slower than other functions. So the limits could be calculated just by determining which function, the numerator or the denominator function, was more dominant. And we took a look at these types of functions. And so we can use L'Hopital's rule to explain now why that works, that why the dominant function will determine what the limit will be as x approaches infinity or negative infinity. So in this case, when g dominates, in other words, g grows faster than f as x approaches infinity, then that means the limit of this quotient function will be equal to 0. And how we apply that is basically using L'Hopital's rule. So let's give me an example. If you remember, we compared power functions such as this and exponential functions such as this. And as we can see, as x approaches infinity, if we were to compute this algebraically, we would get infinity over infinity. Now, some of you may remember that exponential functions grow faster than polynomial functions, which is why our answer, we know in the end, will be 0 for the limit, but we can use L'Hopital's rule to explain that. So if I were to take, because these both go to infinity, and I get infinity over infinity, then that means that I can use L'Hopital's rule, because this is one of those indeterminate forms I was showing you earlier. And so in order to solve this problem, we take the limit, we take the derivative of the numerator and denominator function, and we end up with 2x over e to the x. Well, that still goes to infinity if we were to evaluate this. So we have to take the L'Hopital's rule again and take the derivative of this set of functions, and we get 2 over e to the x. And as you can see, if we were to evaluate this as x approaches infinity, e to the x would be equal to infinity. So we'd end up with 2 over infinity, which is actually equal to 0. So this is why back in pre-calculus we were able to use the fact that how the functions grow faster or smaller to determine dominance in that situation. All right, I think that's it. Please work on practice problems, but if I were to suggest anything, I suggest that you memorize these indeterminate forms, because these are the only forms that you can use for when to apply L'Hopital's rule. Okay? All right, that's it. Thanks.